Well, my talk is about PageRank algorithm and about its different modifications and learning the parameters of these modifications. So I'm going to start with the definition of a web page's ranking problem, and then I remind definition of PageRank algorithm, and I'll tell about its different modifications that account for pages, for different pages and links properties, and then about some learning algorithms of the parameters of these methods, and the experimental part. So we make experiments in Yandex on our data, and that's all. Okay, so first of all, we have a set X of query and pages pairs. So Q is for a query and P is for a page. And we have a function A from X to a set of non-negative integer numbers from 0 to K. Commonly K equals 4, and A of Q and P is a relevance label for a page P to a query Q. And we also have a function phi, so phi, a function f, so f of qp is a features vector. So we have m features, m real-valued features. And these features can be static or dynamic. Static means that they do not depend on a query, and dynamic features depend on a query. And for example, static features can be based on a graph structure only. For example, PageRank is static feature.
Typically, how much?
Excuse me?
How large can be m?
For example, 500 or 1000. And the ranking problem is the following. We want to find such function g, that g of f maximizes some measure of ranking quality, or for example minimizes minimal square error on a training set. Usually measures of ranking quality are discrete, for example NDCG and ERR. So it doesn't matter. I don't want to define these measures, because in our study we use only continuous measures. The definition of PageRank is the following. It is a stationary distribution in the Markov random walk with discrete time on the web graph. So web graph is a graph where vertices are pages, are web pages, and we have an edge from one page to another one if there is a hyperlink from this page to another one. And the random walk is the following. At each moment, a surfer chooses either to move from one page to another by an edge with uniform distribution, and either it chooses uniformly at random a page with probability 0.15. And so a stationary distribution in this process is PageRank, is called PageRank, and it can be computed. It is a solution of the system of linear equations, and it can be computed by the power method. So Pi converges to this stationary distribution, to PageRank, and A is here. A is the matrix of transition probabilities. The problem is that PageRank algorithm doesn't account for some properties of pages and links. It just accounts for the properties of a web graph in general. And we want to account for these properties, and usually it is done in the following way. So let G be our web graph, and Vi be a vector of features for page I, and Eij be a vector of features for a link from I to J. And using these features, we compute weights of pages and weights of links. So, for example, in this paper from KDD 2011, it was done in the following way. So, it's weight F of page I is just a linear combination of its features, and for a link we define a weight in the same way. So then probabilities of choosing a random page are proportional to its weights, and probabilities of choosing random links are proportional to its weights as well. And stationary distribution in this process can be computed by the power method as well. So here I define transition probabilities. And so this algorithm have some problems. So first three are the following. The first one is that some node features are distributed irregularly, and this leads to disproportional differences in ranking scores of neighboring items. Also, some metadata can be sparse, and feature values are noisy, so it causes unrealistic fluctuations of ranking scores. And so the last one, of course, we should have some learning process to learn the parameters of our algorithm. And we propose the solution of these problems. The first solution is to define the nested processes, and it is solution of the first three problems. And the last one, we introduced an algorithm for learning the parameters. So first of all, let me define the nested processes. So we start from defining the weights of our pages and our links, and these definitions are based on two subordinate Markov processes. So first of all, we considered two similar equations with two independent collections of parameters, and the solutions of these two equations are G1 and G2. And using G1 we define weights of vertices, and using G2 we define weights of links. So the weight of a page I is G1 of I, and the weight of a link from I to J is G2 of J. And then using these new weights, we consider the principal Markov process, and our feature is stationary distribution in this process. So we're not the first to introduce this algorithm, because in 2010 there was a paper by Nadaya and Brian Davison. They consider an algorithm called tfresh, and so it contains nested Markov processes. And then we avoid some shortcomings of this algorithm and propose a recency-sensitive model of web page authority. But unfortunately, all these models do not contain any optimization part of the parameters. So also there is an algorithm called browse-rank, which consider continuous random walk on the graph, and so browse-rank is a stationary distribution in this process. It was introduced in 2008, and then we consider a nested process on the graph with on the same graph with continuous random walk, and in 2013, and there was a learning algorithm in this paper, but there was no theoretical foundation of this algorithm. So now let me tell about our best learning algorithm. I'll start from the semi-supervised learning from the paper, from this paper, and this optimization, the optimization problem that was considered by the authors was not direct. So they have pi q of p is PageRank, is our feature value, and s is some linear function of the values of the PageRank. And they consider the following optimization problem. So they find such omega and pi that that this difference is minimal and s is non-negative. So it is not PageRank, but it's approximately PageRank. And as you see, pi q are parameters of the algorithm, so they do not need to find derivatives of pi with respect to omega. And so they use gradient descent. So it's very simple to find the derivatives. And if we want to solve the direct optimization problem, we should find the derivatives of pi with respect to omega. And so we introduce this algorithm. We consider some continuous loss function, and we consider a direct optimization problem. So we want to find the derivatives of pi with respect to omega, and it can be done by the following algorithm. So you can see here an iterative algorithm, and this vector converges to. We prove that this vector converges to the derivatives of PageRank vector. And in this case, we call the final ranking function supervised PageRank. So as I say, we are the first to present this algorithm for computing derivatives of the stationary distribution with respect to its parameters. And so we prove that these vectors converge to the derivatives of PageRank. And in the case of nested algorithms, the parameters also can be found using the gradient descent. So first of all, we consider the second equation and the fourth equation, and so we find the derivatives of our weights g1 and g2 with respect to its parameters, and then we have these weights and we find the derivatives of pi with respect to its parameters from the first equation and the third one. And we call the final ranking function supervised nested PageRank. And now I'm going to tell about the experiment. So we consider discrete time Markov process and the hyperlink graph, which was crawled in Yandex in June 2013. And this graph, so we consider a domain that contains approximately 2.52 billions of pages and 21.12 billions of links. And we consider two different feature sets. The first one is feature sets that was considered in the paper called semi-supervised PageRank, and the second one is temporal features. And our evaluation set contains 127,000 of query page pairs and approximately 16.7 thousand queries. And we choose 90% of the queries for our learning process. And we also use linear combination with BM25 to make our feature dynamic, to make it depends on a query. So the results are the following. As you see, in case of features from the paper semi-supervised PageRank, our algorithm supervised nested PageRank outperforms supervised PageRank with both metrics NDCG3 and NDCG5, and for temporal features as well. We also consider temporal supervised PageRank and temporal supervised nested PageRank, where the jumping factor alpha is not tuned, so we fixed it and tuned all the other parameters. So as you see, these results are worse than in the case of beta alpha. And we learned the parameter alpha, the only parameter alpha of PageRank algorithm, and so it is 0.95. It's extremely larger than the classical one. So here we compare the qualities of two metrics, NDCG3 and NDCG5, that depend on the parameter of linear combination with BM25. And as you see, the pink line is for fresh supervised nested PageRank. It's better for all the metrics, for all the values of the parameter lambda. And finally, we make the experiments that prove that supervised nested PageRank helps to avoid sparseness of data. So first of all, we make our graph smaller. We consider a sample of our graph. So here is some settings, how we choose a sample. And then we make our data sparse. So we simulate sparseness in the data by sampling for each feature R% of pages, where R is either 10, 25, or 5, or 19. And we remove all the values of this feature, of this R% of features. So when R is 10, we remove 10% of the features, and when R is 19, we remove 90% of the features. Well, and here are the results. So the pink line is for supervised nested PageRank, the red line is for supervised PageRank, and the green line and the blue line are for two modifications of supervised nested PageRank. So here we do not wait for the convergence of the algorithm for computing the derivatives of the PageRank. We just make two steps in this algorithm. So we make our data not sparse in two steps, in case of the blue line, and in one step in case of the green line. So as you see, supervised nested PageRank is more stable than the other algorithms. So to finish, I can say that our contributions are the following. We introduce a new model, which is called nested supervised PageRank, and which is based on nested random box. And we investigate an algorithm for direct optimization of weighted processes of PageRank and of nested PageRank. And our experimental results showed that show that the nested algorithm outperforms state of the art. And our future work is to consider different graphs, different types of features, and we also want to improve the speed of convergence, of course, to find the global maximum or the global minimum in the problem, and determine how the numbers of iterations of computing the weights influence the ranking scores and the performance. Thank you.
What do you mean by other types of features? The features are not given?
So I mean that we, in our experiments, we consider two types of features. Temporal one and the features that was considered in the paper, in the previous paper. So they can be...
And still you apply sparse feature selection?
Yeah.
Okay.
Questions, yes, we can put. What is the time to calculate this optimal parameters for the
Type?
learning? Type.
Ah.
How many
Well, for example, on our graph, it takes all the process takes 1 month.
And what about other algorithms?
Well, if you consider supervised PageRank, then it is 3 times less.
But you expect to get better result when you...
So we consider now some not gradient-based methods, and we expect some the increase of speed. Yeah, some increase.
And why you would like to eliminate this sparse features? You say that you need...
So there are a lot of pages. There are some features and pages such that we just cannot compute the features from these pages, or there are some such features that features and pages such that the values of these features are not realistic. So, for example, if we have some queries and pages such as there are no clicks from these queries to pages, we can compute features.
So it's some kind of pre-processing.
Yeah.
You do it at the beginning.
Yeah.
You eliminate all this maybe interesting pages. And what is the percentage of these pages? It's huge.
So in our experiments or
In experience.
so consider 4 different values of this parameter.
Do you have some ideas about adaptation techniques? So don't rebuild the whole, don't learn it at all, but you have some additional pages.
No, we don't know. Think of this problem a lot. Thank you.
Last question maybe.
Yeah. Okay.
How you measure that do you measure the relevance of the pages, or just how to measure the relevance if it is page ranking, and page ranking is page ranking. You have first answer, second, third. Do you measure the relevance of the answer to the content of the query?
So, well, I maybe don't understand exactly what do you mean.
Formal sense means, do you...
So there are relevance labels of the assessors, and they use it, and we use it to find all the values of our metrics in industry 3 and industry 5. So there are a group of assessors that measure relevance, and they make a label from 0 to 4 for each query document pair.
So you get personal page rank, what's called.
Excuse me?
Personal page rank, each one is its own.
Personal PageRank?
Yeah.
And what is with personal PageRank?
It's important too, because they check for each
Yeah.
user.
Yes.
It's considered. Yeah, I see. Yeah.
Thank you.